Are you set?
I'm good.
Right, then we should sing this theme tune. Do 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 bling 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 bling. No,
You're gonna
putting that in. I know.
You're gonna have to do that now. That's gonna be the episode intro.
Oh no. I'm Matt Godbold.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
How you doing?
Great.
It's another Friday. It's another podcast recording day.
Mm-hmm.
And you came to me with an idea already.
I did. I had a thought, which is
Most unusual.
async await and asynchronous programming in general and why we do it and threads and all the things. There's a whole this topic could go on forever, but
like all of our topics, really,
yes.
They're deliberately vague because we haven't really thought about them very much. So
right.
that's the thing. So
yes,
that's interesting. You said async await. Is that how you pronounce that?
Is that not
I would
how
say
you,
async await, and I wonder if that's
async,
a British English thing.
Oh,
you await something rather than await, or is it because you said async? Because
that's just me wanting there to be alliteration. Is that what that is?
I mean, it's alliterative anyway, right? Because they both have an A sound at the beginning.
But I'm trying to emphasize
emphasize, I think,
the alliteration in async await.
So we better say what that is. What is async await?
Async await. Well, it's a programming style, I guess, is what I would call it.
Yeah.
It's a technology. It's a programming style. It's a floor wax. It's a dessert topping.
What's that from?
I think it's like an SNL bit from back in my very, very, very early days. But yeah, it's a solution to a problem, actually.
Okay.
And we should talk about what that problem is.
Yeah.
Which is, if you have a program that has no threads and has no async magic, is just a series of instructions, and that program does things that are I/O bound, like, for example, fetching a bit of data from a remote server, or performing a database query, or even reading a file,
right?
And it is the progress of that program is blocked on that information. It can't go forward until you've retrieved the information that you need. Then your program is sitting there, or the CPU usually is sitting there, doing not very much while you're waiting for this, favicon ICO file to be downloaded from a server somewhere halfway across the world, or whatever it is that you're doing. And so it could be doing a lot more, and you could be getting a lot more out of your computing power by not simply just waiting for it to do that, but by running other parts of your program or a different program or other things.
Well, so taking
happening.
the other side there, just quickly, obviously in a modern operating system, the operating system is going to have other things to do. It's got animating GIFs to keep moving in the background. It's got dancing hamsters, the like. Or other programs will take advantage of your CPU. But if you, as in the user, are running a single program that has a single thread of execution and it is blocked, then you're going to have to wait. And if there's other useful things that program could otherwise be doing, well, they'll happen after the file has come down. Right. Not before. So obviously the normal solution to this is like, I'll make some threads and then I'll have all these complicated mutex and work queues or something. So is that async?
Yeah, no. So I think threads are one solution to this problem, and async is maybe another solution to this problem. But the underlying problem, I think, is that for a single sort of program, you want to be able to maximize CPU time, reduce latency, increase throughput. All of these things can be achieved by just making better use of the CPU. And one way to do that is by having threads. Another way to do that is with async. And I think that either way you go, there are some sort of like head twisting, complicated problems that you can run into. Some might be easier to deal with than others. Some might be easier to test than others. But this is the classic programming technique of solving one problem by creating another problem.
Regular expressions, for example.
Yes, exactly. Right.
Category.
If the R value of your problem growth is less than 1, then you've done a good job.
Yes. But I suppose this hypothetical program that you said that's fetching something or reading a file or doing whatever, the assumption here is that there are other things that program could be doing in order to continue. I mean, let's say it's a word count program and we've given it a list of files and it's got to open up the files, and like naively I would write for each file in list of files, open file F, read every line, count how many lines there are, add them up and print it out at the end. That would be like a not unreasonable way to write that piece of code. But for all you know, there's multiple drive spindles. Some of these things are on the network or whatever. And, you can easily saturate the PCI bus or the network link or whatever if you were doing more than one file access at a time. But you're not. You're just reading one after another. So how do you... The async await is a solution to the problem of, if I know that I have multiple things I could be doing at once, how can I more easily, for some definition of easily, write a program that looks like a kind of normal program still, isn't too far removed from that for loop that I just described, but without tying myself in all these kind of operating system level thread spawning and synchronization issues that I might otherwise have. And so should we talk a little bit about what a straw man kind of implementation of this thing might look like?
Yeah, I think that's good.
So, I mean, if it was this word counting thing, then in one way you could spawn one thread per job, per file, and then let those threads run their separate ways, and then sort of have some kind of collect all the threads together at the end and look at the answer and add those all up. That would be a perfectly sensible way of doing this. But in the async await world, you need a framework that understands how to do input-output operations that can sort of cooperatively multitask. I think that's the key here, is threads means that we're actually using operating system resources to create multiple execution threads at the operating system level. There are literally, potentially multiple CPUs could be involved, and these things could be running at once on multiple CPUs. But that's not the kind of problem we're trying to solve here, because the CPUs are not the problem. It's the waiting for files that's the problem. In the async await world, you are scheduling pieces of work with callbacks. Somewhere deep down in the bowels of the framework, you've said, open a file, but just call me back when the file's opened. Don't block. Don't block.
Like, open the file and read this stuff, but don't wait until you're done reading it to return from that call. Right.
And that's really the trick behind the back of all of these async await, is that now you suddenly have coroutines that are powering this system of sort of cooperatively multitasking all the different things that you want to do in a single operating system thread, one after another, as they become ready. Like the file contents become available, and now your code can operate on it. And then let's talk about like actually what the syntax of that looks like. You typically hence the async await, is that you tag functions of your program as being async, which is a big hint to the framework or language that you're in to say this function can be suspended halfway through and can sort of return early in some way. And then when it hits an await within that async function, what we're saying is do some work, but actually park me here, and when that work is ready, come back to me.
Yeah.
I think the trick there is that sounds a bit like a thread. And logically, it is a thread of execution. There's like a stack, and there's a sequence of instructions that pertain to a single kind of idea that you're doing, a function that you're running. But there isn't an operating system resource associated with it. There's literally just a big list somewhere in a framework of here's all the things I know I need to do when, I don't know, this file read has completed, or this network access is done, or or somebody deliberately yields and says, "Hey, it's someone else's go to run now."
And quite often those things are implemented with an event loop, right? So you'll have basically a queue of events, and then you'll have basically just like a while true loop that is consuming those events one at a time, and then calling back to the callbacks that are related to those events. So you might schedule a file read, and then take that event or take something and say, okay, when this file read is done, generate an event, put it in the queue, and then when that loop sort of processes through all the events and it gets to that event, it says, oh, well, we did this file read. It actually finished about 200 milliseconds ago, but we were processing other events at that time. Now we're ready to process it, so I'm going to call back all of the people that were interested in this and tell them, hey, your data from this file is ready. Now you can do what you want to do. And this has the advantage, like you say, of being able to run in a single operating system thread, so that you don't have to worry about the things that you have to worry about when you're doing multi-threaded programming. You don't have to worry about synchronization. You don't have to worry about threads, clobbering each other's data. And in that way, it's actually much simpler because there's just this whole set of problems. And, I will tell you from personal experience, loving tests and wanting to write tests for these kinds of things, it is quite difficult to write tests for multi-threaded code that truly give you confidence that the multi-threaded code actually works 100% of the time.
Right.
It's quite easy to write tests that convince you that it works, and it only works 99% of the time. And then you find, oh, actually, no, yes, there is this one case that I didn't think about that it can not work. So from that standpoint, it has, it's kind of attractive.
Absolutely. I think that's a really good way of phrasing what's going on. Like at the nuts and bolts level, there is, as you say, an event loop. There, on a Unix-based system, there's probably a select loop that's got all the file handles of all the things that are going on. And then as they become ready, as you say, things are woken up. And described like that, it puts you in mind of, say, how JavaScript and Node.js do all of their work with actual callbacks. You say file.open, file name, comma, and then call this function when the file has opened, and then you end up with this very deeply nested callback, because once the file's open, your function is called, which then wants to read, and then of course that's another asynchronous call, and before you know it, you've got like 18 levels of indentation, or you've got 200 disparate tiny little functions, each of which then calls another tiny little disparate function. And that was how JavaScript was for the longest time. Async await specifically, so you can have an event loop and you can have this callback type thing without async await, but async await is at a language level feature which hides under some level of syntactic sugar that callback based thing by kind of writing callbacks for you. When you say await file.read, what's really, quotes, happening is something like the function that you're in the middle of is cut at that point and turned into another function, two functions, like the bit before the await and then the bit immediately after the await. And the bit immediately after the await is essentially turned into the callback function for the file.read. And so you don't need to think of it in these terms. You don't need to nest things further and further and further. Your code for an individual, like I'm the line counting function, just says file equals await file.open, file name, something like async for line in file.async read lines, count ++, return count. And so you've just written code that looks almost exactly the way that we described for the single-threaded case, with just a couple of magical keywords like tagged in there. Behind the scenes, the whole thing is rewritten to be callback-based or futures-based or some of the other techniques that they use. Promise-based, exactly.
Yeah.
And it makes for, as you say, a much more testable design because it is not subject to the whims of operating system time slices or multiple CPUs actually executing multiple code paths at the same time, which threads would be. It's only when you say await blah does your logical flow of instructions stop and someone else could potentially get the use of the CPU. So you kind of have to be aware of that under more advanced techniques. Like if you share a cache for a class and you have multiple like async awaits of your class going on at the same time, you have to be aware that every time you await something, then potentially the cache could be being used by by someone else. But it's so much more controllable, and it is deterministic, which I think is the key for things like tests.
Yeah. And you can still get things like race conditions in both paradigms, right? Like you can have things that are racing. They're either racing across multiple threads or sometimes racing to the top of the event loop.
Yes.
Right? Like depending on which events get into the queue first, you might have code that's executed in different orders.
Right, and oftentimes frameworks don't necessarily specify the sequence in which, like, if there are two things that are ready at the same tick of the clock, who goes first? In which case, again, that can be something that can be exposed by tests where you're trying to puppeteer time and the completion of things.
Yes, usually a lot of both languages and frameworks are intentionally vague about how that's going to happen.
Right.
But yet sometimes accidentally consistent, which sometimes will trick you into thinking that you have code that runs properly when actually there are cases where it doesn't. But yeah, I think what's interesting is that there's and you sort of touched on this a little bit, is that there are levels to this. There's like I'm just going to do a non-blocking call with a callback. Right, like that's like the most basic level of this. There's no async await syntax sugar. There's not even necessarily like an event loop. There's just I'm gonna, the sort of select statement is sort of the classic example of this. Is I'm just gonna do a non-blocking I/O call, and I'm gonna have some facility that allows me to say when this is complete, call me back over here, but this initial call that I'm making, I want you to return immediately, right?
Yeah.
That's like the lowest level of this.
Good old Ewood block in Unix.
Yeah.
Hey.
Right. And then I think one level above that are things like futures and promises and things that you're not doing anything special in the language. You're not introducing new keywords. You're not doing anything there. What you're doing is just creating, objects essentially.
Placeholder objects.
Yeah. That allow you to make it a little easier to work with these kinds of callbacks, right? Where, you can call a function, the function will return immediately, you'll get some object back that represents the sort of thing that you've scheduled to happen, and you can interact with that object in interesting ways. Obviously, you can just, apply a callback and say like, hey, when you get my data, let me know. You can also gather a bunch of them together and say, when all of these are complete, let me know. You can gather them together in ways that say, if ones fail, we'll then call this function, and if some pass, then call this other function. And you can do interesting things with that as well, but that requires no language changes or language support or anything like that. That's just, objects essentially. And then a level above that is going all the way to sort of full, sort of like, yes, we're going to introduce new keywords into the language. We're going to bake the sort of asynchronous, non-blocking I/O things into the standard library of the language. Mm-hmm. And we're going to make this sort of like a first-class citizen within the language. Node.js obviously is a great example of that because they just took something that had already been in web browsers and were like, all right, well, we're just going to lean into this real hard and start building other things out of it. Obviously, you and I have written a lot of Python recently, and Python 3.6? Is that what
something? Yeah, 3 and a bit.
3 is when they introduced the sort of async I/O and introduced those keywords into the language. But you can also just use like a third-party framework. Like I certainly used EventMachine for Ruby for a good long time, which isn't really async await. It's more of that sort of second level that I was talking about.
Right, with futures and adding callbacks to the futures or something. Or
it's really it's like there are futures, but it's like 1.5 even. It's sort of like, but the interesting thing about it is it sort of spawns this whole separate non-blocking ecosystem. And one of the things that you'll see a lot in the Ruby world is that you have like the Postgres library, and then you have the EventMachine Postgres library.
Yeah.
And they're only kind of related to each other. And that's because like
same in Python, right? You've got like Postgres and AIO Postgres for the same reason.
Yeah.
And I think that's one of the more insidious is a little bit of a bad word to use, but like one of the things that happens when you start having async libraries is that you get this separation, and because it's all pervasive, anything that async library calls that itself might need to be async also needs to be async. Yeah. And that's like keyword level down, right? Like, suddenly you end up with, read file and async read file, because they are very different operations, one of which returns the contents of a file. The other one returns essentially the promise or a future of a file. And you end up with this a bit like, I say this in like C++, once you start introducing const correctness in one place, suddenly everything needs to be const correct because you can't, it won't let you not be. And it's the same with async. As soon as you get to a point where you can't do something asynchronous anymore, you're like, well, now we're blocking again.
Yeah. We had this running joke for a while there that it's like the glitter of the programming world. Like once you start using it, it's brilliant. Like it just gets everywhere, right? Like you can't.
It's got a half-life of measured in millennia. You never get rid of that last grain of glitter. Never really get it. Or sand from the beach.
Yeah, microplastic. It's the programming microplastic. So but it has a lot of advantages. But you do sometimes get into this day where it's like, oh well, that means this needs to be async, which means this one. I'm just going to rewrite the whole thing at this point. Yeah,
everything's async, and you feel like you're just scattering the async keyword everywhere.
Yes,
and that's not without cost.
Yeah.
But before we move on to like things like cost and how it's actually what's going on under the hood a little bit more, I was going to sort of make the observation that I don't think I made clear when we were talking about the word counting example, right?
Mm-hmm.
We've written these like individual async functions that count the number of lines in a file by async opening it and then async for each reading lines or however that works. But then you mentioned gather as like a primitive operation, and that is a key to actually unlocking the multiple outstanding IO requests at once.
Right.
So in this instance, one could write the code at the top level that says for I in each of the files I want to word count, async await that word count of file 0, running total plus equals that. But you would still be back in the world of single file happening at once. You're just doing it asynchronously, and that event loop hasn't got any other work to do. So it'll just sit there and go, okay, I'm literally in select now, blocking for that file to become ready, and then I call you back, and then you're no better off. You're slightly worse off. But the gather primitive operation you talked about takes a bunch of future objects of some description, be they promises or futures or coroutines or async whatevers, and it says, okay, all of these, we want to kick them all off at once. Again, there's not any threading, so it doesn't actually happen at once. Each one is run until it gets to a point where it yields.
Yeah.
But then I come back and do the next one, and the next one, the next one, and now I have multiple IO requests in flight, and then whichever one of those comes back first, I will service, and it goes into the event loop, and now that file is open, and so that coroutine is starting to process the first file or the second file, and so on. So that is the equivalent of spawning threads at that point. That's how you get the parallelism, is by gathering a bunch of async awaitable things. And I think that's another thing to sort of bear in mind, is how coroutines interact with this, because languages that don't have coroutines or something like coroutines becomes a difficult thing. I don't actually. You mentioned Ruby, and I don't have any experience with Ruby specifically. I know Python had coroutines before it had the async and await, and they were able to be like library level solutions to async await just using coroutines. And I know that the async sort of decorator is a spin on always forcing an object, a function to return a coroutine, as opposed to being a function called in its own right. So does Ruby have a similar thing? How do you, or was it, you did mention it's like level 1.5, so maybe it didn't have the same.
Yeah, I mean, if it does, I'm unaware of it. When I was using it, EventMachine was entirely like a third party thing.
Right, it was basically not a language extension, so it didn't need
not at all
coroutines. And again, another sort of aspect that makes writing this kind of code more tractable are languages that allow you to do arbitrary captures into lambdas and unnamed objects and things. So either you can use those as the callbacks and not worry about who owns what, or you use coroutines themselves. So yeah, I suppose what I'm winding up towards here is that why do other more low-level programming languages like C and C++ not really, with a big asterisk footnote, have async await type operations, even though all these other programming languages we're talking about are written in C or C++, right? So there's got to be a way of doing it.
Yeah.
And, really, I mean, so the trick there is coroutines are a huge unlocker. They're the thing that allow you to suspend a function and carry on again a bit later on in that function. I know I described it as it being syntactic sugar for like cutting a function into two functions. And there is a way you can do that. And I believe the first version of C# that introduced this had that kind of rewriting technique. Behind the scenes, it was just literally rewriting the code as blocks of follow on continuation functions one after another. But modern times, these are coroutines that can yield. That means they literally say, hey, I'm not finished yet, but I'm going to return a value to my caller. And that value to the caller indicates that, yeah, I haven't finished. So go do something else, and then you can call me back, and then it will continue from where I left on. And in that traditional classic coroutine sense. But the problem with that is that you need to be able to keep around all of the internal state of a function between calls to that function. You need to be able to suspend and resume.
Right.
Going back to our original like operating system level threads, that's what the operating system knows how to do, and it's its meat and potatoes.
Right.
It knows how to suspend a thread and page in, switch in a new thread, restore all the state from that. And at an arbitrary point, it's kind of like a hostile takeover, right? At any point in time, the operating system can say, you've had enough CPU now. I'm just coming in. I'm saving your registers. You'll never know that I'm about to start using the CPU for something else. And later on, you'll wake up dazed and confused and won't even know what happened.
Right.
And what the coroutine does is says, like, this is a cooperative choice. I need to be able to preserve enough of my state at this point for you to continue doing some other piece of work. But then when you come back to me, I can continue where I left off. And for interpreted languages, that's usually as straightforward, and I'm going to use air quotes that our listeners can't see, as storing the interpreter state for that function up to some point where you don't need to store higher up. Maybe that's where the event loop started or whatever. And then you can resume by just jumping back into the bytecode with that kind of information around. And usually they're garbage collected as well. So anything that you had references to will still naturally exist because they still have a reference count, or they still have something pointing at them. So you can just carry on in C and C++, you have the problem of, well, it's arbitrary assembly instructions, and the compiler needs to know how to hang on to things like the stack. And there is a single stack. It is the stack. It's not a stack. When you have multiple threads, you have multiple stacks by default, but in a coroutine, you deliberately don't necessarily want that. It becomes more complicated. So then to the footnote, the big asterisk I said earlier, coroutines are now here for C++, but it is the beginning of the process. So the really interesting way that coroutines have been brought into C++ is that the keywords co-await and co-yield, and I'm sure there's another one. Gosh, I can't remember the other one now. They are in the language now, but they're sort of batteries not included. They're very, very low-level primitives that the language is making promises. And then the STL, the standard template library, does not yet have much in the way of support scaffolding for you. So if you want to write coroutines, you can roll your sleeves up and write a whole bunch of like complicated state management code, and you can do it. And there are also some cool libraries that do some of this stuff for you. But the expectation, as I understand it, is over the next couple of cycles of the C++ committee, every 3 years meeting, then the sort of predominant best solution for a whole bunch of things to do with execution and other things will come to the fore, and that will become the way that we think about these coroutines and how they exist in a bigger, in a wider context. And then once those building blocks are in place, maybe there will be some async routines and async libraries that we can use, which will be great. So obviously, it's just me steering it my way there to talk about my own thing. Which, and again, I've seen people use the co-yield and co-await stuff in sort of like toy examples, but I've never used it myself in anger. And although this is not async await at all, because coroutines are separable from async await, you can build async await with them. Coroutines are really, really cool for things like writing emulators where you want multiple very lightweight processes. Think every single device wants to have, hey, another clock tick happened. And you want to be able to write code that looks not like the traditional, poll. Everyone's written poll where you have like a state machine in every single element on that's being polled, and the state machine is like, hey, every time you call poll, you have to do switch. What's my current state? Oh, case waiting for this. Oh, okay, well, then I guess I'll do this type of thing. And it's really convenient to be able to just do write like a video chip that just says, await next cycle, draw 2 pixels. Await next cycle, draw 2 pixels in a for loop that's as wide as the screen, and then you do and now do the thing that happens at the edge of the screen. Await another cycle, and you just write straight line code like you were the video chip, and there was no one else in the world except every time there's a cycle, you say, okay, I'm done for this clock tick. Now someone else gets a go, and you don't want to use threads for that because the synchronization cost is staggeringly high for that, and the work that you're doing in between them is tiny. But it's inconvenient to write the normal poll stuff. So anyway, that is a complete aside, and I've not yet written a coroutine based emulator, but I would like to.
Yeah.
So let's sort of go back to some of the other languages we were talking about earlier. I know we have spoken about Java before now. Is there an equivalent for Java?
I'm a little embarrassed to say that I don't know.
There's nothing embarrassing about not knowing things.
Yeah. I don't.
We should make that clear.
Know. I feel like I should know this. That's why. I mean, there's lots of things I don't know. Let's be real clear on that.
Oh, right. Okay.
But I feel like as much as I've done with the JVM and with asynchronous programming, I've never. I guess doesn't Clojure have like an async? I think it does.
So there must be a mechanism for it. And
again, well, I mean, to your point, it's like you can build these things on top of lower level languages and they work just fine. But I actually don't know if there's one in Java. The one point that you made me think of though when you were talking about the sort of the C++ introduction of this is that I would imagine that means that the C++ community and standard library is going to face the same situation that is true in Python, that is true in a few of these other languages that have introduced this, where you sort of get this bifurcation of the standard library into like, well, these are the like asynchronous, non-blocking calls, and these are the star-bellied sneeches, and they're between the two, you kind of don't want to cross, and so you sort of have to make your choice. And if you have to go back and sort of retrofit it, it sucks. But it in a lot of cases means you either have to spend a lot of time figuring out how to unify the duplication between those two worlds in a way that makes sense, or just duplicate it. We're just going to do everything twice, the async way and the sync way. And that can definitely be create confusion and make it harder to use things. But if you want to be able to take advantage of this, that's what you need to do.
Yeah, I don't know about that actually. I know that the Boost library ASIO, which is the asynchronous I/O library, is one of the things that's been talked about for being standardized as the network library of C++, and maybe part of the reason why all these things are taking longer than people thought is that there is this kind of unification discussion going on. And I don't know much about that myself, but I'm sure if we found some people, we could find some people who wanted to talk about this kind of stuff. But I'm very much more a user of C++ than anyone too deep in the details of how it's designed. But and I know that this is the kind of thing that people think about a lot, and that's one of the reasons why, arguably, the C++ standard library is mostly, I was going to say impoverished. That's a terrible, but it's a pretty impoverished standard library when it comes to actual pragmatic things like opening files, reading every line of a file or whatever. It's kind of there's this very high level concepts now and algorithms that you can use. If you want to do some of the more obscure partial sorting of an arbitrary array that's not even an array, it's just iterator pairs of things. You can do all these clever things, but if you want to find the full stop at the end, or if you want to trim the last character off a string, then you just have to do it using those algorithms. You don't just have a dot remove last or whatever, or dot uppercase and dot lowercase. All those kind of niceties don't come, but mainly because they aren't necessarily as general purpose as one might imagine. Like, what does it mean to be uppercase? Well, what locale? Oh, now you've got all these questions, right? A lot of other languages go, nah, but we just want to print something out in shout caps. That's important to me, not like the general. So I think that is definitely a factor in the slower adoption of these new technologies, is because they want to do it right, knowing that it kind of has a certain persistence. It stays on for a long, long time. There is, it's worse than glitter for the C++ committee. They have to make decisions that are basically forever decisions. They never really go back on stuff.
Yeah. Another point that you made that I wanted to briefly touch on was the sort of performance impacts. And I definitely have made the mistake myself, and I've seen other people make the mistake of sort of just throwing threads at a problem when they have a performance problem. It's like, I'll just break the work up and distribute it across threads, and then it'll be faster, right? And the answer is not always. If the cost of crossing those thread boundaries is higher than the actual amount that you save by breaking up the work and the cost of reassembling it when you're all done, you can actually make it slower and more complicated at the same time.
Yeah, brilliant.
Which is not great. And so, one of the advantages of having a sort of single-threaded, event loop style, whether it's with async keywords or not, is that you don't have to pay not only do you not have the sort of programmer complexity problems of crossing thread boundaries, but you also don't have to pay the performance hit of crossing thread boundaries. And if you can sort of structure your work in such a way that you can, take advantage of the non-blocking I/O while keeping the CPU busy, you can actually get like very good throughput by doing that. And sort of avoid some tricky performance problems of like, why is this queue every time I go to read from the queue and it blocks? Like, it really slows things down. I keep the queue full, and even when I keep the queue full, it still slows down. What's going on here?
I think
kinds of things.
It's an important distinction you make there. Like, if you are predominantly I/O bound, then you can definitely take advantage of a event-based system, because like you said, like if you're keeping the CPU busy, then sort of by definition, when the CPU is finished doing whatever it's doing now, there's always something new for it to do, because some other I/O event has completed it, and someone who was waiting for a read has now got it, or someone who was waiting for a write to drain has got the okay that it's gone. But it's easy to fall in the situation, and this is what Compiler Explorer suffers from, right? If you hit Compiler Explorer, some of the work that it does on the event thread, so like the web server itself is running like this. Everything in Node.js, which is what Compiler Explorer is written in, is continuation passing style mostly, although we're slowly moving to async await actually. Style of work, which means every web request is like an I/O thread as far as we're concerned, I/O response. Every now and then, when we've actually got the results of a compilation, so for us, another piece of I/O is we ran the compiler, it's another process, and as far as we're concerned, we're awaiting it now. So like we can be serving more web responses, we can be giving the favicon.ico to whoever wants it, and then when the compiler is finished in its own process somewhere else in a little sandbox, we're going to read the results back in, and we're going to parse it so that we can give something back to the web browser that's renderable. That is totally CPU bound, and for like large programs that have 20, 30, 40,000 lines of assembly output, it can take us a long while. Meanwhile, we are essentially blocking any other web request that's coming in that's unrelated to that for that one node. Now, we have load balancing, we have multiple physical computers that are doing the work, so that's less of a problem, but our CPU is 100% wedged, and we can't do the other work that is available to us. Now, if we had threads, that would not be true. And so we've discussed having worker threads for exactly this thing, in which case, actually, just to sort of square this off, we would probably kick off that parse the assembly output and return me like the dictionary that I need to send to the user. That would be a worker thread, and then we would await the thread coming back. We'd like, hey, kick off the thread and then await the results, and now we're back in the land of async await. It's just just like running the compiler, the result of parsing the output becomes itself an async I/O inverted commas thing, at least as far as we're concerned. So there are kind of ways of making everything fit together. I think the other thing I think about with performance, you mentioned about crossing thread boundaries, as it were. Obviously, thread boundaries are typically not very expensive in the general sense because they're in the same process. You can actually affect the same memory as the other things.
Yes, for good or for evil.
For good or for evil, exactly.
Yes.
So obviously the locking is where it starts to become more troublesome. And you mentioned queues, so you did sort of cover that exactly as one would want. But that hidden inside that queue is a lock that is going to prevent you from being able to do work once it's either full or there's no work to do, all those kinds of things. Or, you've got the possibility of deadlock and other issues like that. But conversely, if you are in async await land, and with gay abandon, you're putting the async keyword on every single function you can find, even when there isn't any actual awaiting inside of that function, then you're pessimizing your program, because behind the scenes, what that means is that when you call that function, you don't actually get like the nuts and bolts that function which returned an integer now returns a future of an integer. And you call it first of all, and you get back like hey, there's nothing to do yet. And then it gets scheduled on the event loop. Or it could, at least if someone's awaiting it, right? Now it's going to be scheduled on the event loop, which means there's at least one tick of like the event loop clock before the first line of your function is going to start running. Or it's actually, it depends on the implementation. Some of these things do actually eagerly execute. And there's a difference between tasks and async things in different languages or whatever. But I've at least had definitely some experiences where I've called a function and gone, why did that not do anything? And you realize, I didn't await it, which meant that all that happened is it called the function to generate like the coroutine context. And then we're like, okay, here's your thing. When you want it, it's ready.
Yeah, here's this code that I can run for you whenever you like.
And you're like, but I called it. You're like, you didn't call it. No, you didn't.
No.
So there's...
You told me you were going to call it.
It's not as cheap to do that. You're creating these intermediate objects that have some setup cost, as well as the actual, maybe you're going once around the horn of the event loop before you're actually making progress. Now, that does have some positive side effects. If you are CPU bound and you're just trying in a really naff way to yield up. So this is another Compiler Explorer anecdotal thing here, and I hope that none of my developers who are actually good at developing code are listening, who contribute code. This is my harebrained ideas. But one thing I consider doing is literally putting async await sleep 0 into that big parsing loop. Every 10,000 loops, just to yield it back.
Yeah.
And it's of course it's awful, and no one should do that. But it's a way of giving someone else a go at the CPU.
Yep.
So that at least some progress can be made on those web requests that are coming in.
Yep. You asked me earlier about async await and Java, and I don't really know. But one thing I did see earlier this week that I thought was super interesting is a proposal for Java virtual threads, which might be an interesting middle ground between these two worlds that we're talking about. And the proposal, as I understand it and remember it, basically revolves around threads that, when you're executing, blocking what would normally be blocking I/O calls within the context of a virtual thread, the JVM underneath the covers will turn those into non-blocking calls for you.
Right.
And suspend the execution of the virtual thread to allow other virtual threads to execute, which means you don't have to do the thing that you normally do with threads and pool them. Sort of, you never want to spawn thousands and thousands of threads at the same time, because your operating system threads, because you're going to starve out the operating system and make the thread scheduler's job significantly harder. But with virtual threads, you can just go ahead and make as many as you want, because they're not mapped to operating system threads.
They are essentially async awaiting automatically at the point where the JVM says, hey, you called file.open. Well, rather than file.opening, I'm going to rewrite that as an async await kind of thing and let another virtual thread take over this thread, capital T thread, like this,
capital
whatever
T
execution thread, well, however that's word. But obviously you kind of need to opt into that a little bit higher up somewhere where you spawn these virtual threads. Right. And each one of them is essentially a top-level coroutine. Or a asyncable thing. That's a neat solution that doesn't require much change to the code, and you're still writing straight line code. As far as you're concerned, you're still blocking, and you are blocking, right?
Yes.
It's just at the point where you would block and rely on the operating system to context switch you. The JVM says, I can context switch you much more cheaply.
Right.
And I'll do that here and get someone. Yeah, that's awesome.
Yeah.
That's really
and one
clever.
interesting side effect of that I was thinking of is that it avoids this problem that we were just talking about, where you sort of bifurcate the standard library.
Oh,
right?
Yeah.
Like you're just saying, no. Underneath the covers, it might be bifurcated, but that will never hit the API. You will never see that.
Really
right?
interesting.
It's all one thing.
Yeah.
Which is kind of cool because it just sort of reduces the cognitive load on programmers who need to understand how the standard library works.
No, that's super awesome. Yeah, that's a really interesting observation. I hadn't thought of that, but yeah, that bifurcation is otherwise a big deal breaker for a lot of people. They're like, oh, which one? Which way are we going to go? Oh, no, that's super cool. To finish on, I just want to make a couple of observations that amuse me, and that is all these async await style things, and again, mainly the coroutines that help them be more useful are the way that operating systems used to work. I don't know if you did you ever do any Windows 3.x development back in the day?
No. Windows NT was really the first operating system that I used as a programmer in anger.
The Windows and the Win32 API, which is still around and about, has like an event loop, right? And I don't know if you've ever looked or remember. Do you remember did you do any raw Win32 API stuff even in NT? Because although it wasn't the way I'm about to describe it, it was the same API.
Yeah.
So you would do you'd call a getNext event effectively, and you'd have a switch statement on getNext event. So you do switch get message or whatever I actually can't know. WM get message. Does that ring a bell? I'm making up like stuff because
you're reaching into the very depths of my neurons here, but yes, that does actually ring a bell.
And then you'd pass it all these structures to fill in, and it would return the why, what's the next message, right? And it would be WM paint, and then you'd be like, oh, I better draw
or like a mouse click event, right?
Or
like
a mouse click, or any of these things.
Yes.
So in modern times, that's just reading off of an event queue, right? Your thread is goes to sleep. And you can have many threads. Obviously, they can do any other things, but your sort of UI thread is there just reading the next message off of that. So as the mouse is moved through your world, or if people are clicking or typing or whatever, you get those events. But way back in the dawns of time, that was how the operating system gave someone else a go. You call get message, and it's like, oh, I'm suspending you now. There is no preemptive multitasking here. At this point, we're saving all the registers, and we're going to load someone else's registers and memory map, and then we're going to return to their get message, and now they get a go on the CPU. And certainly the operating system that I was using prior to Windows, which was RISC OS, had that feel too. You would have to do this system call that would tell you what the next thing is, and then really it was switching and returning to somebody else, which was a really interesting design because you could do that in user mode. It wasn't that difficult to see how it was saving all the registers and reloading them all back out again. And so you could write your own cooperatively multitask sort of sub-threads within your thread using the similar kind of techniques, which was a great way of introducing this is how the operating system must be doing it. And I remember having an epiphany moment doing exactly that, and just having those two routines that would, call a function, which isn't really calling a function, because the calling that function actually jumps back into and returns from the other function's call a function, and then you can ping pong backwards and forwards between the two of them, and it's just one of those crazy things. So it's kind of come back now, this cooperative multitasking, which is why I described it as that right at the beginning of this whole conversation. It's it's cooperative multitasking. You get to say when someone else gets a go of the CPU. Yeah.
Everything old is new again, my friend.
Everything old is new. Well, we've covered some things that we are inexpert in, only as users. Yes. So I do hope that anyone listening to this who's been shouting at the microphone, at the headphones or the speakers,
I'm sure our
about
listener is very frustrated by now.
So do tweet us at TWOSCP to let us know all the mistakes we've made, as per usual. And until next time, my friend.
Yep. Next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at twoscomplement.org. Contact us on Twitter at 2CP, that's at WWOSCP.
Theme music by Inverse Phase. inversephase.com.